And this is crazy. So here's my... Oh, thing's on again. Alright, so this will be the last new section that I'm making a video for this year. It's about the central limit theorem, which is kind of like the whole point of this chapter. Central limit theorem is really good stuff. Why does that thing keep doing that? Central limit theorem is a really good thing to know as you move on to your next phase of mathematical experience. Here's the questions I'm going to be putting up at the beginning of class. And there's a lot of terms here. Like, look at the question number 3. If you want your mean of a set of sample means to get closer to the population's mean, what does that mean? You know, I mean, how many times can I use the word mean in one sentence? So there's a lot of stuff going on. And I talk about that, first of all, in the list here. I've had a list of terms. If I use this mouse, it would be better than the pen. Here's a bunch of terms right here, just right here in the middle of the notes. Everything from sample size down to sampling distribution, I guess, is the last one. Sample distribution is kind of the title of the section. But some of these get really sticky, like the standard deviation for a set of sample means, and the mean of a set of sample means, and the sample means, and the numbers. I mean, it's kind of crazy. Okay, so what I started out talking about here on the top of these notes about how I'm going to do the activity on page 670. So I ought to just do the activity on page 670. So get your book out. I'll wait. Okay, it's talking about, well, first of all, you know what, before I even do this, I should be talking about what kind of data are we even talking about here. This is a little bit of a departure of what we've been doing. We're talking about finding averages of numerical data, which we kind of haven't done for a while. We've kind of been looking at binomial distributions for a long time, and standard normal distributions for things like, you know, somebody's height or the variability of a certain type of output or something like that. But this is all about, let's go around and ask everybody in America what their favorite number is between 0 and 9, and we're going to find the average of all those numbers. Or, you know, so we're going to go around and find out how many cars they own, and we're going to get a whole number from everybody. We're going to average those together. It wouldn't have to be a whole number. We're talking about long lists of numerical results and finding averages of those, and doing averages for that when the entire population is impossible to probably actually know, and you want to take a survey or a sample of some of those and see how close you get. Now, what's at play here is we're getting a little more fancy now. It's not just go out and take a survey and see how close, you know, see, the more people you survey, the closer you're going to get to the actual data, because we're talking about stuff like sending out a bunch of, say, surveying minions. Like, say everybody in our class goes out and asks 100 people. I keep saying that in here. 100 people each for everybody in our class goes out and asks 100 people. So we have like, say, 17 samplers in our class, but the sample size is each 100. So we're going to sort of split up the job into 17 of these 100-person surveys, and then we'll talk about the means that every person comes back with from what their 100 people they asked, and what the actual population is. Anyway, I think that's enough to sort of set up what's going on. On page 670, they talk about setting up this experiment, and I did it with this autograph software, which is not a software you have on your computer, but it's okay. It's just, I just want to show you the phenomenon that's sort of going on here. All right, you could do this by hand. They want you to do it by hand in the book on page 670. The first thing I want you to do is generate a list of random numbers. Now, I made a list of random numbers here using the software. It's got 100 numbers in it. Okay, and then I graphed that on here. It's actually the red dot plot, but I zoomed out so much you can't even see it. Let me see if I can get that back, because then we're going to talk about this purple one and this blue one and what that's all about. Can I zoom out? Oh, I can. Okay, great. So here's my numbers. You can see them in this red stuff. When I did numbers 0 through 9, how come I didn't get any zeros? I'm sure I got zeros. Maybe it's because it's the axis here didn't graph them. Anyway, were there zeros? Maybe there wasn't zeros in the list. Anyway, it doesn't really matter because they wouldn't add to the average anyway. I may have done that wrong, but it doesn't matter. We're going to see the phenomenon with the purple and the blue stuff down here the same way. So these are the results I got. I got so many 1s and so many 2s and a lot of 3s. It's not really normally distributed. It's kind of random, which you'd expect with a random number generator. And then the first thing you're supposed to do, this is in step 2B. Run this simulation 25 times. Or sorry, I do 4 numbers at a time, and each time I take an average, and I record that average, and that's what the blue set is. That's what's called the sample means. So I found the average here. So this is how often those average happened. So the scale here looks a little funny. But you notice the blue picture here is when I did, and I collected it over here somewhere. Number and sample mean 4.8. I think this is it. Am I reading the right thing here? Oh no, that's about the raw data. Here's about the first thing I took was the sample means. I took a sample size of n equals 4. I took 25 of those samples. So I was looking at I looked at the first 4 numbers and I found a mean. I looked at the next 4 numbers and I found a mean. Actually, it wasn't even 4 at a time. No, I'm sorry, it's randomly. It's random samples. It just takes 4 of these numbers, 4 of the red numbers, finds their average. And I did that 25 times around the set of red. And yeah, 25 samples, so chances are I could have asked everybody, but I don't think it actually does. And it gives you all this stuff, because here's all the different means I got, and you notice they're all divisible by quarters because I did 4 at a time. The mean of all of those is 4.97. So we're kind of looking at this going, okay, if I take the average of these averages, I might get kind of close to what the overall average is. The standard deviation among these averages is such and such. Okay, so then it says, well, do that again, but do it for what happened there. Can I undo that? Oh, I can. Yeah. Do that again, but let's take larger sample sizes. So now I have this little tiny, now notice the relative frequency is way lower, but now I have this purple one. What they did there was, what they asked me to do on that one was, let's make the sample size 15 and take the average. So now I got some wackier fractions. Now I'm taking 15 of those red dots at a time, finding their average. And you notice these are a lot closer together than they were over here. This is when the sample sizes were all 4. Now they're 15. The average of what I found, yeah, was the average of the averages here is a lot lower than the average of the averages here. Also, what's really significant, which really tells you something here, is the standard deviation in this list is way smaller. These lists of averages are less likely to be spread apart because I took a larger sample each time. So these means aren't going to be as wacky as these were. When you just take 4, if you just ask 4 people, you might get an average that's way off. See, like I got a 7.25 here, or 7.75. I got a 3.75. I got a 2.75. Oh my gosh. Here, they're all between like 4 and 5.4, I think is the biggest one. So they're all like tighter grouped, and the average of these averages is something I should probably believe better than this. If I did this right, and I actually had numbers between 0 and 9, the overall average ought to have been, now I only did 100 pieces of data, so it's not going to be perfect, which is kind of their point. But you would expect the overall average is going to probably be something close to 4.5. And you notice the sample, the average of the averages here is closer to 4.5 than this one was. Okay, I'll show this in class again, and you can see what's going on. Okay, so the terminology that goes with all that. The sample size was the number of people that you're going to go out and survey each time you go take a survey. In the example we just did, it was the 4 and the 15. The size of each sample before you even take any averages at all. Sort of the base level sample. How many samples are you going to take? I was doing 25 in both those. This actually we're not going to mess with very much. The number of samples is not that big of a indicator of trends like sample size is. I just put number of samples in here, and actually they don't even have a really a variable for this because it's not that big a deal, the number of samples you take. It's the sample size that starts to get important. Okay. Sample means. When multiple samples are taken of the same size, you take the mean of each and get a set of means. So it's like when we take the each one of those sample means. So like we're looking at this. This was the list of sample means. It says sample means at the top. Why is that little thing following me everywhere? It's the pen thing. The list of sample means is all this. So the first time I looked at 15 red dots and found their averages is the first one I got. So there are going to be 25 sample means in this list. So I guess I don't know if the range was really what I said before. It looks like there's a 3 point something. And maybe something bigger than 5.4. Yeah, there's a 5.4, whatever. So there's going to be 25 sample means here. This is the average among groups of 15 randomly selected red dots. All right, so are you getting confused yet? I got sample size, sample means. Population mean would be the actual mean of the whole thing. I'm talking like I'm typing here. It's whatever the actual sort of unknown mean was of the original red. Oops, I should go down this way. The original red set, whatever the averages of all these red ones. And I usually don't have any way of figuring out what that is, so that's why we're doing all this sampling, so I can kind of get some data and kind of guess at what the average of these red ones actually is. Like the average number of cars in the entire U.S. population per family, I don't really know what that is. There's really no way to tell unless, I mean, like perfectly, unless you actually knew exactly how many cars there were. But that's what that refers to. The population mean is the real truth that's out there that you're trying to uncover. All right, mean of a set of sample means. Okay, that was the average of these averages, and this one turned out to be 0.48. So that's, once you're used to getting sample means separate out from population mean, this isn't too bad. Even though it's got the word mean in it twice, getting sick of hearing the word mean. The mean of sample means is, yeah, you take averages of all these little minion-y surveys, and you find the average of those, and you get a mean of a set of sample means. The sample standard deviation, same sort of thing. Once you've gotten all these, whoa, what happened there? Once you get all these little means here, these means of your 15 length surveys, this list produces a mean and it produces a standard deviation. It's like, how fuzzy is this list? And the smaller this is, you know, the closer you're getting to the real population mean. Okay, and what we got? Population standard deviation would be the actual standard deviation of the red dot list, the standard deviation of how many cars there are in American families, which you probably never get exactly, but that's what that's referring to. Standard deviation for a set of sample means. Oh wait, I think I talked about this too soon. Oh man, you're gonna kill me. Sample standard deviation would just be the standard deviation within one sample. Standard deviation for a set of sample means was the thing I was talking about before, which is the standard deviation among this list. Standard deviation in one sample, I don't see here. The standard deviation, yeah, okay, actually it is. It's 2.8. Is that? I think that's the population standard. Yeah, that's the population one. Standard deviation within this list, I have no idea what it was. This only tells me the mean for that, so it didn't even show me. That's why I didn't talk about it. But then the standard deviation for all the means, it's the standard deviation between the means and how spread out the means are. I was right. This sigma is the population standard deviation. What the actual red dots standard deviation picture looks like. Can I just drag this out of the way? Will it just like, no? What is it? Okay, I'll mess this later. Sampling distribution is at the end what this little graph looked like of all the distribution of how the samples turned out. Can I get back to this? So the blue one you can kind of see looks like this. Looks kind of symmetrical, although there's still a lot of stuff right around 4. But once I started taking bigger samples, notice the peak is lower. But it really starts to look more like a normal distribution, and that's what the central limit theorem is all about. I believe I'm going to run out of time before I get to do any problems, so I think I'm going to have to split this into 2 parts. Actually, I take that back. As I look at this and look at the questions and look at what you have to do for homework, it's fairly conceptual. It's not a lot of calculation anyway, so maybe I'm kind of already there. These are your questions you're going to have to answer at the beginning of class. I have to get to a couple of these things. So let's talk about the actual central limit theorem. Central limit theorem itself, I've hinted at some of its stuff, but as you get a bigger sample size. As I decide that, okay, if we're all going to go out and ask 100 people, let's change that to 200 people each. And we come back and compare what's going on. As we get bigger sample sizes, all this stuff happens at once. 1 and 2 are easy to believe. 3 gets kind of wacky down here. Okay, there's your calculation. Yeah, 14 minutes. I think I'm going to split right here, and I will see you in part 2. Okay.